Hi guys, my name is William Schlageter, and I'm going to talk about superoxide dismutase. This is superoxide dismutase, and so is this, and so is this. All three of these enzymes take two superoxide radicals and change them via a metal-mediated dismutase reaction into hydrogen peroxide and normal diatomic oxygen. A dismutase reaction is a reaction that takes two identical molecules as reactants and makes two distinctly different products. The metal which facilitates these reactions is different in each enzyme. The enzyme we'll be focusing on is manganese superoxide dismutase, which uses a manganese catalytic center. Considering the entire cell, manganese superoxide dismutase in humans is found exclusively in the matrix of the mitochondria. Other superoxide dismutases are found in the cytosol of the cell or the extracellular space. Recall from Bio 252 lecture this figure. Oxygen in the mitochondrial membrane can spontaneously reduce to a superoxide radical by oxidizing quinone. It is specifically this superoxide formation that manganese superoxide dismutase spends the majority of its time dismuting into hydrogen peroxide and oxygen. As was discussed before, without this dismutase, superoxide radicals would build up in the mitochondria and shut down the powerhouse of our cells. Now let's get a little more specific about manganese superoxide dismutase's structure. Notice that this enzyme has two identical subunits. It is a dimer. This area of the enzyme is what contains the active site. Notice that this active site is a fairly deep pocket of the enzyme. This ensures that the manganese center doesn't just react with any substrate willy-nilly. In fact, there are several positive residues in the immediate area around the pocket, here. These positive residues attract negatively charged superoxide radicals towards the active site of the enzyme. This is part of how superoxide dismutase ensures specificity for its substrate. Let's get a closer look at the active site. But this is still a little too frilly, so we'll cut them all away and just get to the important residues. The central atom is manganese. It is being held in place by these three histidine residues, 26, 74, and 163, as well as aspartate 159. The active site available for the dismutation is actually this hydroxide molecule. Rather than run the risk of letting a superoxide permanently inhibit the manganese center, this enzyme uses the hydroxide as a middleman to transport electrons from the radical to the metal and back. When a superoxide radical enters the active site, it gives an electron to the hydroxyl, which in turn reduces the manganese center from 3+ to 2+. While accepting the electron, the hydroxyl group also binds to a nearby proton, creating a water ligand. And the superoxide just becomes your stereotypical diatomic oxygen. Next, a second superoxide molecule enters the active site with another proton in solution. It takes an electron and hydrogen from the water ligand. The ligand then oxidizes manganese back to 3+, and it becomes hydroxide once again. Thus, the overall reaction is this. Let's notice something interesting here. Since all manganese superoxide dismutase does is move around a couple of electrons, one can calculate the reduction potential of the reaction. Reaction A is merely the opposite of reaction 1, and reaction B is the same thing as reaction 2. Since the first reaction has a reduction potential of -0.18 V, and the second reaction's reduction potential is +0.91 V, it makes sense that the electrons will proceed in this reaction. However, when considering the reduction and oxidation of manganese, we find the actual reduction from Mn3+ to 2+ to be +1.54 V. This means that if manganese was reduced by reaction A, it would not give up its electron to form hydrogen peroxide in reaction B. In order for this reaction to be favorable, manganese would need to have a reduction potential between -0.18 V and +0.91 V. Conveniently, the reduction potential of manganese superoxide dismutase has been experimentally determined to be +0.3 V, which is right in the range where we want it. This is all well and good, but look at the difference between these reduction potentials. They're both manganese, so then what on earth is changing the reduction potential so much? Well, maybe the adept viewers have noticed that the residues in the active site I haven't mentioned yet. What's happening is a chain of hydrogen bonds between aspartate 159, the hydroxide ligand, glutamine 143, tyrosine 34, histidine 30, and another water molecule in solution. Their interactions look like this. Together, these hydrogen bonding interactions lower the reduction potential of the manganese center to be plus 0.30 V in the perfect range to dismute superoxides. This is all fine and dandy, but does it matter really? What can we learn from manganese superoxide dismutase? Well, with the other two superoxide dismutases we mentioned before, even when the genes that produce them are deleted, we can still function as people. However, when the genes for manganese superoxide dismutase are deleted, death occurs within days of birth. Out of all superoxide dismutases, the manganese one is essential to life. Not only that, but functional manganese superoxide dismutases give cancer the boot. In novel studies, manganese superoxide dismutase is injected into tumor cells, and a high proportion of tumoricidal cancer cells is observed. This is because hydrogen peroxide in the mitochondria is actually a signaling molecule to produce tumor necrosis factor, which in turn signals the cancerous cell to undergo apoptosis. And that is superoxide dismutase.